Hello, myself Mursal Ayub Hamdani. I am here to present my paper for NewSOD 2022. My paper is selected under the topic Novel Material and Devices with serial number 11. The title of my paper is Highly Efficient and Novel Lumped Michelson Modulator using Vertical PN Junction Based Phase Shifter. These are the contents of my presentation. I will start by introducing the area of investigation. The novel CMMM, that is Common Mirror Michelson Modulator structure proposed by our group, is discussed next. The integrated interferometer modulators usually imply horizontal or vertical PN structures, and these are discussed next. Finally, RLC circuit based small signal lumped element model is put forward. We compare our work with the existing literature work, and finally the references. The advanced data centers employ silicon photonic transceiver, first introduced by company Lextera, as plug-in switches. These transceivers are based on integrated optical modulators of A, resonator-based structures, and B, interferometer-based structure. The former have a compact footprint, while as the latter has the advantage of higher bandwidth range of operation with lowered temperature sensitivities. Due to obvious advantage of interferometer-based optical modulators, our group focused on the interferometer variants. In literature, Mach-Zehnder modulator and Michelson modulators are the most common for silicon photonics. Now, for a given doping profile of the phase shifter and a given value of delta L, that is the path mismatch length, the MM based modulators had a lower value of V pi L pi, which made it a clear add-on. The integrated modulators in silicon photonics come under two design variants: traveling wave design and lumped element design. The traveling wave design allows for a high baud rate of greater than 60 Gbps for the silicon based modulators. However, the traveling wave design suffers from optical and RF mismatch, RF loss at higher frequency, and obviously better baud rates for lithium niobate and indium phosphide are already available. Now, this makes our choice for a lumped element design, which has higher density of integration but at a lower baud rate. So, recent literature survey clearly reveals that silicon will be preferred only for higher integration rate rather than high baud rates. So, that makes the advantage of lumped element design clear. In figure 1a, a general Michelson interferometer structure is redrawn. The mirror in each arm is implemented via Y branches with a closed loop. In figure 1b, we report the modified and the novel common mirror Michelson interferometer wherein the two arms act as inputs to the DC loop, which acts as a common mirror for both the arms. You can clearly see the difference between 1a and 1b. Using then figure 1b, we design a modulator as shown in figure 1c, with each arm surrounded by p-n doped phase shifters, which are used to change the effective index of each arm due to the applied bias, leading to a phase shift and finally optical modulation. In figure 2a, the two PN variants are shown, that is the horizontal PN and the vertical PN. As can be clearly seen, that VPN allows, that is the vertical PN allows for a large overlap between the optical mode and the PN junction. It thus increases the value of the delta N effective for a given V bias change, leading to a higher junction capacitance, as can be clearly seen in figure 3a. The higher delta N effective with respect to V bias change allows for a higher phase change with respect to V bias, and that is also clearly shown in figure B, that is figure 3b. From the values of phase shift, we evaluate V pi L pi and plot it in figure 3c. A low V pi L pi for a given V bias is clearly seen for the value of VPN. The phase shifter can be modeled as a RC low pass filter with 3 dB roll off frequency plotted with respect to V bias in figure 3d. Figure 4 now clearly shows RLC circuit as a lowered element model for the proposed CMMM. CSG, signal to ground, and L, the inductance of the electrode, are independent of the doping profile of the diode of the phase shifters. So we take experimental values from general MM designs in literature and take this as our case study. Now by plotting the frequency response of the small signal model of the modulator, we get the electro-optic response of the CMMM, VPN and HPN as shown in figure 5, with VPN showcasing a lowered 3 dB bandwidth. Then optical eye diagrams at different bit rates using PRBS31 signal pattern with 3V peak to peak, 3 volts peak to peak without pre-emphasis. As can be clearly seen from figure 6 at the top, for horizontal PN junction, by lowering the value of the source impedance, we can increase the value of the extinction ratio at the same value of speeds. However, if ZS is kept as 25 and we move on to VPN, we can clearly see a higher extinction ratio as at 35 Gbps. Now, if we increase the value of speed to 50 Gbps, the extinction ratio gets lowered to 3.84, but it can be clearly seen to be comparable with the HPN. So, clear advantage of the vertical PN. When we compare our reported work with the existing literature, we can clearly see that the 3 dB bandwidth is lowered. However, the VPi Alpi figure of merit is the best reported. And high ER of 3.84 at 50 Gbps is also considered to be a good result. Now, as we can conclude that VPN based CMMM has better VPi Alpi at reduced bandwidth, and ER is higher for a given bitrate and ZS.